we have an incline and a ball. If I release the ball, of course you can't see the ball because my hand's in the way. If you release the ball, it rolls down the incline. We're trying to determine maybe why. Now, when the ball is on the incline, there are various forces acting on it. So what are those forces and how would they appear on a free body diagram? Well, here's a free body diagram. Here's the ball on the ramp, and we see that gravity is acting downward, and we have a normal force acting in this direction, perpendicular to the ramp. Now, when people draw this, they want to draw a couple of extraneous forces. Now, there could also be a frictional force, and people have indicated that on some of their attempts, and that's fine, that's good, and most people that did that right. But we're going to ignore friction right now. There isn't a whole lot of friction. Well, there is friction involved in this, but it's kind of subtle. There's not a lot of rolling friction. Okay, so we have the gravitational force down, normal force acting perpendicular to the incline. Now, a lot of people want the gravitational force to be down and the normal force to be straight up. That's not the case. We've already seen with the demonstration with the domino and the meter stick how the force exerted when you push something down into an incline acts perpendicular to the incline. So the normal force is perpendicular to the incline. It's not vertical unless the incline happens to be horizontal. Then people will want to have some kind of a force here that's making the ball go down the incline. And that's intuitively, that's probably what I would have done if I had been asked to do this at this point of the course. There is no such force. The only forces that act are the gravitational and the normal force. If there's a force like this, where's it come from? Think about it. Is it some kind of magical force that just appears when you do an incline? Well, you know, our intuition would be consistent with that, but we need to refine that a little bit. So we'll see in a minute where the force comes from to accelerate the ball down the incline. We want to draw a free body diagram. Now, this isn't a free body diagram, actually. This is just a picture of the ball on the ramp with the forces. Free body diagram, we're going to represent the ball just by a dot. And we have the force of gravity acting downward here. Now that force has this little yellow squiggly line through it. And I'll explain that in a minute. But we have the gravitational force acting down, and we have the normal force acting perpendicular to the ramp. We choose to orient our x and y axes parallel to the ramp and perpendicular to the ramp. Having done so, we see that the gravitational force has components in both the x and the y direction. The normal force has component only in the y direction. There's no x component because, of course, the y-axis is perpendicular to the x. If we try to project this to the x-axis, it just projects right back to the origin because, of course, the projection goes from the tip of the vector perpendicular to the line on which you're projecting it. Okay, so we have these projections. We'll call this F grav x for the gravitational x component of the gravitational force. We'll call this F grav y. It's not gravy, it's grav y. Although people, as soon as I pointed that out, started calling it F gravy. Okay, well, I might use that because I think it's kind of funny, probably doesn't hurt anything. Okay, just along we understand that F gravy is the y component of the gravitational force. Now, under these circumstances, well, what's the acceleration of this ball in the y direction? Okay, well, the ball doesn't accelerate in the y direction. It's at the same y position all the way through because it's moving along the x-axis. So it has no change of position in the y direction, so it has no zero velocity in the y direction, and it follows that it has zero acceleration in the y direction. The ball does not accelerate perpendicular to the ramp. If it did, it would come up off the ramp, or it would go down through the ramp. So, and that is the reason we chose the x and y axes to be in this direction. We chose the y-axis to be perpendicular to the ramp because we know there's zero acceleration perpendicular to the ramp. That was the motivation for this orientation of the coordinate axes. With also a very good reason for the x-axis to be parallel to the ramp, because that's the direction in which the ball does all its moving. Okay, so zero acceleration perpendicular to the ramp means there's no acceleration in the y direction. And from that, it follows that the net force in the y direction is zero. Now, if the net force in the y direction is zero, what does that say about the normal force and the F gradient, the y component of the gravitational force, the component of the gravitational force perpendicular to the incline, okay? Or y grav y. Now, F grav y, okay. What does it say about those two forces, though, if the net force in the y direction is zero? Well, clearly it says that these forces have equal magnitudes, but they're in opposite directions. And we can write that out in terms of the definition of net force. The net force in the y direction is equal to the normal force plus the y component of the gravitational force. It follows then that since F net y is zero, that the sum of these forces is zero, and the normal force is equal and opposite to the gravitational force. And at this point, I was going to put arrows over these to represent the fact that they're vectors, but we're talking about just the y direction, so a plus or minus sign will suffice in this case. Okay, so anyhow, we got the normal force, just the y component of the gravitational force, and that's fairly easy to understand intuitively. Gravitational force pulls in this direction. Its pull in the y direction is this, and that's why there's this normal force, because this component of the gravitation compresses or slightly bends the ramp, causing the ramp to push back with the normal force. Okay. Now, the x component of the gravitational force, that's the only force we've got in the x direction, unless there happens to be friction. And if there is friction, it's easy enough to incorporate that into the picture. So the net force in the x direction is the x component of the gravitational force. So your net force on the incline has these components. It has F grav x in the x direction and 0 in the y direction. So the acceleration vector has this component in the x direction, the net force in the x direction, F grav x, divided by the mass, and component 0 in the y direction, meaning that the net force is just this. Now, one important point. Okay, I have the gravitational force, then I drew the components, the x and the y components of the gravitational force, just by projecting the gravitational force onto the y-axis and onto the x-axis. At that point, I drew this little wavy yellow line to indicate that I'm throwing away this vector, although it's still in the picture. It's not really there anymore. This is just the vestige of our gravitational force vector, and I've replaced it by the two component vectors, because the gravitational force vector has exactly the same effect that the two component vectors would have. So, again, the two component vectors in the y direction add up to 0. The net force is just our F grav x. And we'll summarize by drawing a third diagram. They seem to be right angle challenge. That angle is less than a right angle. This angle is more than a right angle. I think this one is actually maybe fairly close. I think it's a little less. Okay, these are supposed to be right angles. I'm looking at the board from a weird angle and not being all that careful, unfortunately. But anyhow, I can then replace this picture, since this vector and this vector add up to 0, with just this picture that has only this one vector, the F grav x, which is now your net force So your acceleration is going to be that net force. One other comment, if we know the angle of this ramp, then we can easily find the angle of the gravitational force vector with respect to the positive x-axis running along the ramp. This angle here and this angle here will be identical. So if we just add 270 degrees to this angle, we'll get this angle. Now if you drew the ramp going downward in this direction, then your x-coordinate or your x-axis would be here, your f-grav would be here, and the angle would appear here. Okay, this angle would appear here. So you would get a different angle than you get here. And the reason I mention that now is if we know the weight of this or the mass of this thing, we can figure out the gravitational force on it. And then we can multiply it by the cosine of this angle to get the f grav x. We multiply it by the sine of this angle to get the f grav y. And we can determine the normal force. One other comment, a frictional force is dependent on the normal force. So it will be necessary in a lot of cases to calculate the normal force, so you can multiply by the coefficient of friction to get a frictional force, which would oppose motion. Okay.